Right, it's time for carbohydrate reactions. Next segment will be disaccharide reactions. And here it comes. You'll be starting with an L sugar on yours. I know it's not natural, but that doesn't mean it can't happen. We have to draw L idose. So please find D idose on our useful information page and draw its mirror image here. Yeah, a new faculty member just came out of the restroom. That was sarcasm. It was a student. They should be talked to. Okay. All right. Yeah, distractions. Don't believe that's on a video, but it happened. Where is my useful information? Right there. Okay, idose. Down here. Just remember, the D version goes left, right, left, right. So the L version, mirror image, will go right, left, for the hydroxyl. Right, left, left. Remember that. Right, left, left. Right. I don't need to see the H's. As long as it's a nice Fisher form. Right, left, CH2OH. 1 point. And then it says some enzymes are going to convert that to alpha N-acetal of 2-aminopyranose. So I want to remind you, carbon 2 is no longer an OH, it's an NH on the same side. So it'll be an NH, but it'll also have an acetal on it. Carbonyl, CH3, and pyranose. And you've been doing these 100 times, so you know all the steps, and you can get to the final answer by now, right? All right, so that's going to be there. And it's going to be alpha, so the anomeric O is trans to the CH2OH. We now have an N with an H and an acetal here. And that's carbon 2. It's down, then up for the OH. And I realized I did something wrong. It's down for this OH. And when it's an L sugar, I didn't do my steps properly. And the rotation didn't put that up, put it down. That means my alpha's wrong now. I know. This is the one where the biology teacher is wrong. Not all biology teachers. Why in this sugar is alpha up when your biology teacher told you alpha is always down? Well, the definition of alpha is this is trans to this CH2. It's not about up and down, it's about trans. And we finally have the right sugar. So we got that. Now enzymes took the same thing and made this thing to a beta-3-O-benzylfuranose. Oh. And that's going to be using this O right here to make a furanose, is this one. And that's going to be a normal rotation, putting carbon 5 at the up. So here we go, pink. We just have to decide how that works out there. That's carbon 5 up there, by the way. Now, if you rotated it, you get two ways to think about this. Is the OH still on the left after you rotated it, or is it on the right? I don't know. I know if it was S before, it better be S now. And it was not R before, so it was S. And it better be S now, so it goes 1, 2, 3, R. Hey, it's on the right now. Yeah. And carbon 4 got rotated to put this O here, the pink O. So I've got a red dot, should have a pink dot. Heck, it is pink. There you go. Carbon 3 is here, 5, 4, 3, 3 up left. 2 down right. I know I didn't finish what I was doing. Beta, cis. Hey, it's up again. Look at that. And I got to put a benzyl on the oxygen on carbon 3. Reminder. 1, 2, 3, 4. Hey, maybe you haven't seen this before. Italicized O is the same as italicized N, except it says put the group on O. Here it says put the group on N. Hey, we didn't know that. Now we do. So carbon 3 does not have an H. Has a benzyl. And be careful with short forms in this section. I'm not going to take any chances. I'm going to draw the world's smallest phenyl here. I didn't do it very well. Skinny pen. There. And then we're supposed to do what? Well, this thing's a dead end. This thing is going to go with reagents to make this thing. Stereochemistry ambiguous. Don't do this with your answers. So that's not fair. What's going on? That's the question. Ooh, this looks a little like something we saw earlier today with an acetal here. We had a student do a presentation where she made stuff like, she had stuff like this in her molecule. Similar. It's an acetal. There's the O benzyl. It looks like we just need to make an acetal from this OH and this OH. And remember, this is just the open form. The closed form is always in equilibrium with the open form. So you don't have to show me how that happens. But you do have to provide the chemical that made the acetal. Well, you've got the 2 alcohols, which are always required to make an acetal. You need the carbonyl compound that made this acetal, and it's right here. This thing that had 2 bonds to O. Was that. There's the C right there. And a catalyst, sulfuric acid. You could write enzyme if you want. Oh, yeah, let's do that. There you go. Need some kind of catalyst, right? You're going to write sulfuric acid, I don't mind. Toluene sulfonic acid, don't mind. And this one is saying, I want you to convert this from the aldose to the ketose. And if you don't know how that happens, is it goes by way of the ene diol here. So the intermediate that would do that would be this intermediate. And yeah, feel free to do this. That doesn't change. R. And ketose is a ketone here. And that becomes OH up there. And then what's the difference between this and this? Well, the benzylic ether is gone. It underwent hydrolysis. And how we got a ketone here, I don't know. That's a good, there's a lot of good stuff here. Wow. Yeah, 3 points. Hint, protection is necessary. Oh. So not only is the benzylic ether gone, clearly, carbon 3, but we made a ketone from only one of the alcohols. Oh, 2 of them. This one and this one without oxidizing our aldehyde. Well, no, we're not there. We're here. So we've already got our ketone number 1. That's this one. We got to oxidize this to a ketone. I like it. Without oxidizing this primary alcohol. Oh, that's a pain. So the question is, how do you oxidize secondary alcohol without oxidizing this primary? I'll summarize here. How do I oxidize this to get to this without also oxidizing this, because I want that to stay the same? So it says protection is necessary. I got to protect, then oxidize, then deprotect. Any suggestions? Nope. Okay, well, we can protect alcohols as DHP reagents with CHP, but I want to warn you, DHP doesn't survive the conditions of chromic acid oxidation, but it would survive PCC. Now the question is, if you treat this thing with DHP, it'll protect both alcohols if you're not careful, but it'll do the primary one faster, less hindrance. So give me some kind of protection. How about 1, DHP hot, 2, PCC to oxidize the secondary that didn't get protected, and 3, now you got to deprotect the DHP and the benzylic ether. Wouldn't it be better if I just had 2 benzylic ethers? Then I can deprotect them both at the same time. So maybe 2 benzylic ethers, and same logic, KH, or how about lithium N, oh yeah, 2, BrCH2 phenyl. Why did I choose that base? I want to take the H off this H, but not this H. Why would this H come off first with that base and not the blue one? And the answer is, this one's less sterically hindered. And then that makes this 3. And the thing I like about this the best is H2 and PT, like we saw in last test, does hydrogenation of the benzyl ether to get our molecule back. Once again, that's some hard points. I want to skip that one. Here it's all about, can you draw me the fissure for an alderic acid? So the fissure you've already got drawn from before, only a slight change. And you got to remind me what an alderic acid is. Down right, up left. Just draw what you had before. OH, OH. We had an aldonic acid where the aldehyde got oxidized. We had a uronic acid where the bottom carbon got oxidized. We have an alderic acid where both get oxidized. There's your summary. So I need OHs on the top and bottom for an alderic acid. And then I want a cyclic anhydride. Oh, anhydrides are made from 2-carboxylic acid. So it's going to be a big old ring. Oops, what am I doing? And there's your 2-carboxylic acids. It goes, how many carbons in between? 1, 2, 3, 4. 1, 2, 3, 4. Bottom one, OH. We're not allowed to be ambiguous. You know, I'm having my thoughts on that. You get 1 point for that. 2 points if you figure out wedges and dashes on that thing, but I don't think that's worth your time. To make everything R and S the way it's supposed to be, look at the key for how to do that, but I don't think that's the good use of time. We want to make lactones that are delta and gamma, alpha, beta, gamma, delta. So alpha, beta, gamma, or alpha, beta. Oh, you can't make the gamma lactone for this carboxylic acid. Watch, alpha, beta, not an alcohol. Can't make a lactone unless you have an alcohol. So you got to go from the top one, alpha, beta, gamma. And same ideas about stereochemistry. Alpha, beta, gamma. So what's on the alpha position? Alpha is an OH. Beta was the OCH2 phenyl. Gamma is an OH. If you want 2 out of 2, you got to have the proper stereochemistry. This doesn't. And I need the delta lactone. I don't think you can use the bottom one. Alpha, beta, gamma. No, you can use the bottom one. You can use the top one. Alpha, beta, gamma, delta. You can use either one. I'll take either one for the delta lactone. So I use the top one here. Alpha, beta, gamma. No, I didn't use the alpha, beta. Yeah, I did. Now I'll use the bottom one just for variety. What I did there. And delta lactones are 1 carbon bigger. Alpha, beta, gamma. Uh-oh. How did I get to an epsilon lactone without even trying? Got the Greek letters in the news lately, huh? Omicron. Omicron's in the news. You notice that? Too busy studying organic chemistry. All right. Well, it's a Greek letter. There's Omicron, micro being small, and at the end of the alphabet, there's omega, mega being big. They're both in the Greek alphabet, and they're near the end. All right, so what's on alpha going from the top? OH, OCH2 phenyl, OH. You know, I think I lost the last CO2H. I used this one on the bottom one this time. Alpha, beta, gamma, delta. Delta has a carboxylic acid sticking off of it. And in my previous one, I used the bottom one, alpha, beta. I used the top one again, alpha, beta, gamma. And gamma had this. Gamma has this. What else is on gamma? Alpha, beta, gamma, gamma. Gamma has an OH. Gamma has a C that goes to an OH with a CO2H. I had the wrong molecule. Sorry about that. Yeah, much better. And moving along, singing our song. We're already at overtime here. We have to draw alpha furanoside, and here we have the beta furanose. So very similar. No benzyl on this one. So copy what you got here without the old benzyl. Got your OH here. You got your normal OH there. You got your now if it's going to be alpha, it's got to be down because it's trans to C here. And it has to have a nitrophenyl glycoside. So draw a phenyl on there with a nitro in position 2, and it says show all pi bond. Oh, just my fancy way of saying I wanted to see if you can draw a nitro group. And there's a nitro group. That's a minus charge on the O sticking off of nitrogen there. And there's your, yeah, there you go. And the answer actually showed up here. This is an acetal. Acetals don't do normal redox reactions. So the answer here is no reaction. And then I'm going to use acetone in excess. That's what this says, acetone in excess. HOTS and DST. And it says to make acetals using, hint, one of the acetals uses alcohols on carbons 5 and 6. That was 5 here, 5 here, 6 here. And I guess the other acetal has to be the other two. There you go. I wouldn't say one of the acetals. This says diacetal. That's right. I was implying diacetal. All right. So here's the deal. Code pink. Up O, down O. Don't draw the H's on there. You've drawn it once, don't draw it again. And here's the red. I like acetals of acetone. They're easy to draw. See how I drew the acetals of acetone? Just make a big X. There's the carbon from acetone. There's the methyl. There's the carbonyl. And bingo. TCC excess. Every alcohol get an oxidized to ketone, ketone, ketone aldehyde. Here's the words. Sorry, here's the picture. I gave the words. And OR. And that's the end of that. We'll do one more video, overtime video coming up for disaccharide reaction. Maybe.